In this video of Fundamental of Electrical Circuits series, we're going to focus on Y and delta connected sources and loads in the context of the three-phase circuits. And actually our focus would be even narrower than that. We're going to be focusing, strictly speaking, on a balanced three-load circuit. So before I get too much into the details of it, one thing I wanted to spend a little bit of time talking about is how is a power created in a three-phase. Now it's more sophisticated than that, but at its very simplistic view, you have a generator. Generators are made out of windings. And in this particular case, they have three separate windings that are equally spaced around a circular area. This is not quite circular, but circular enough. So if you want to balance one, these three windings should be exactly 120 degrees, centered around 120 degrees around the circle. And then in a sense, you have a magnet that has a north and a south, and this magnet is spinning. So what do I have here? I have a generator. If it's a nuclear plant, I'm going to heat up the water, create steam, and run it through a turbine that makes this winding turns. If I've got a hydro, the water falls on a turbine, makes it rotate. If I've got a wind, the propeller makes it turn. Anyway, you can kind of see the picture that these magnets with the north and the south are spinning. As they're spinning, they are producing basically a plus and a minus sine wave coming out of each one of these. And they should be, if their windings are exactly the same and they're spaced equally around the circle, the sinusoidal signal coming out of these three should be exactly the same in the same direction. Everything should be identical. Okay, so we've got three sinusoidal coming out of this, and then depending on how we connect these things, we will end up with two different configuration fundamentally, and in each one we could have a positive sequence and negative sequence depending on how we connect it. But in a sense, by correctly connecting the pluses and minuses of these sources, we'll get the different configurations. So as far as the source configuration is concerned, we could either connect it as a Y connected source, okay, and a Y connected source basically kind of look like a Y. So you're going to have a source sitting here, you're going to have a source sitting here, and you will have a source sitting in here. And in this particular case, we connected all the minuses to each other. And then the positive side we pulled out. Okay. Now, to be complete, not only are we going to have these voltages of VA, VB, and VC, and hopefully you'll see that the way we did this, we basically took all the minuses and connected them to each other and pulled the pluses and called one VA, one BB, one is VC. And depending on what sequence you use, you're going to either end up with a positive sequence or a negative sequence. But to be complete, we also have to add what we call the generator impedance to these things, or winding impedance. They give it all kinds of names, but let's use the winding. So this is going to be a ZW equal to RW plus JXW, where R is the resistive value and X is the reactance of the circuit. And they should all three of these should have exactly the same if you want it to be balanced, right? VA, VB, VC have to have the same frequency, have to have the same magnitude, and have to be 120 degrees out of phase. And that is accomplished by putting these three windings at 120 degrees apart from each other. And of course, this will have exactly the ZW, which is exactly the same as that. And this will have a ZW, which is exactly the same as that. So now we've got our sources. And if you see our sources, then the naming scheme is also predetermined by the convention, where this place, if somebody says what is VB prime, so let me rename it. So this little point is referred to as with a prime, so we know it's this location. That's inside the source because we haven't included the impedance. This would be C prime, and this would be A prime. Okay, these are labeled B, C, and A, indicating we are including the impedances that are naturally part of your source. Okay, so that's that. And now what do we call this? We call this point the neutral. And we represent it with a small n. So this is really important because that is, excuse me, that's one of the benefits of Y connected, because you have safety where there is supposed to, in a perfectly balanced circuit, because all of these voltages add up to 0, this point is 0 volts by definition. So the neutral terminal is a safety one. Okay, so in order for me to transmit the full circuit, in this case, I'm going to need 4 wires, because I need to have the neutral line, I have to have the A line, B line, and C line. The other option is delta connected. And the delta connected is more or less the same, and as the name implies, it's going to be connected like a delta. So you're going to have your source minus plus. So what's going to happen when you look up here is that the plus and the minuses get connected to plus to minus, plus to minus, plus to minus, and that's how you get a delta. So delta, again, the Z winding still is going to be the same as we did before. So Z of winding is going to be R of winding plus J times X of winding, whatever that is. Okay, and then this would get connected to plus minus. It's going to have its own impedance, of course, and then we'll go to this one, and this have its own impedance, of course, which is all, since we are doing a balance one, they're all going to be exactly the same, and this is going to have a plus and a minus. So notice how plus is connected to minus, all that. And in this particular case, then the same points are there. It's a C, a B, and A. And you might wonder why they have delta connected and Y connected. Why not just have one and be done with it? Well, if you're in the generation side, or you are in a factory using 3-phase, it's really nice to have Y connected, because you're going to have the neutral side, so you could have the safety of that. If you're but on the transmission side, it would be really nice to have a delta connected, because of course you save yourself from having to have a N. There is no neutral here, as you notice. There's an A, B, and C, but there's no N because they never got connected. So if I'm doing transmission, I only need 3 lines versus 4. It might not sound like much, but that's a saving of 25% or 30%, depending on how you count it, because you're eliminating a line. These lines are very, very expensive to pull for thousands of miles. So yes, it's worth converting from Y to delta and then back from delta to Y when you want to use it, just to save that wire. All right, so this is the source. Of course, you got the source. You're going to transmit it over a bunch of wires, and then on the end, you're going to use it. And your load, so this was sources, right? You can also have the same conversation of what kind of load you have. You could have a Y-connected load, or you could have a delta connected load. Now, again, the idea is pretty more or less the same. And again, if you want to have a balanced circuit, they better all be the same. So we usually refer to as Z delta, and then we represent it as some R value of load plus some J times some reactive part of the load, and then you have another Z of A here, which is exactly the same as that one. And to make it look a little bit like delta, at least, here is your delta. Now in delta, these are delta. And to stay with the convention, they usually refer to these points, the load points, with capital letters. So you always say this is A, this is B, and this is C. When you come over here, it's the same concept, except the loads, yeah, you're still gonna have Z. This time we're gonna refer to it as Z of Y. Z of Y is gonna be, of course, R of Y plus J X Y. And again, since I want to have a balanced circuit, all three loads better be exactly the same, or else it will not be balanced. And that's what we are striving for always, is to get a balanced load. So you got three of those, and again, but in this case you also have a neutral. This fourth node is referred to as a neutral load, so you're going to have not only A, B, and C, but you also have load. Now, as you look at this thing, you say, okay, I've got a source, got some transmission line, and I've got a load that's I'm going to use. So I've got source, transmission. So I have got two sources. They can be either Y or delta, and they got two kind of loads. So the question is how many. So just make it a little smaller so you can see it. So you got four possibilities. Now the question is how many possible transmission if I can spell transmission circuits can you have? How many different possibilities can you have? Well, I could have four. If you think about it, I could have a Y source, and this Y source could be going to a Y load, or this Y source could be going to a delta load. Okay, I could have a delta source, and you can kind of see the picture now. Could go to a Y load, or we could have a delta source feeding through a transmission line a delta load. So these are the possible cases a transmission system could be set up under. You could have various kind of source feeding various kind of loads. This is probably one of the more common ones we encounter. Both the source and the load are Y, but there could be different variation. That brings us to the end of this particular video, where we talked about sources and loads in the context of Y and delta connected formation in a transmission environment.